Here's a puzzle. 5 people share one Netflix account. The plan allows 4 streams. All 5 press play in the same second on different continents. Exactly 4 must get through, not 5, not 3, every single time. Welcome back to Design Netflix. Episode 1, we build, continue watching. And the big lesson there was that eventual consistency is usually fine. A slightly stale resume point hurts nobody. Today's episode exists to break that lesson. Concurrent stream limits is one member-facing flow where eventually correct means wrong. By the end, you will be able to walk a race condition frame by frame, fix it atomically, and the part interviewers really probe know when to fail open. Let's go. Let's make the problem concrete because the details matter. Meet Kumar family, one premium account which allows 4 concurrent streams. It's 8 am, dad starts a movie on the TV, mom opens her laptop, kid 1 is on a phone, kid 2 is on a tablet. 4 slots filled one by one, and when kid 3 hits play on desktop, too many streams. That's the product working as intended. But here's the actual engineering question. Those 5 plays didn't arrive politely, one by one. They landed within milliseconds of each other. Something somewhere had to decide under true concurrency and get the answer exactly right. That decision point is this entire episode. Before any architecture, we need to name why this problem is different, because on the surface, it looks like the same system as last episode. Same members, same devices, same press play moment. In episode 1, if your resume point was 2 seconds stale on another screen, literally nobody could tell. A stale row is invisible, an error page is not. So we chose availability over consistency, and AP store Cassandra, eventual everywhere, and that bought us a million writes a second. Now run the same stillness through today's flow. The counter says 3 streams active, but it's 2 seconds behind reality. 5 devices, each read 3. Each one passes the is 3 less than 4 check, and all 5 start streaming. A stale counter doesn't produce an invisible glitch. It produces an oversell, and an oversell of a paid limit is a revenue bug, a contract bug. So here's the staff level move, and honestly the thesis of this episode. You don't pick a consistency model per system, you pick it per flow, and you say the boundary out loud. Resume points, eventual, stream slots, strong. Same product, opposite answers, both are correct. Requirements phase 1, and this system is exactly 3 jobs. Job 1, when a member presses play, check their active stream counts against their plan's limit, and if there is a room, reserve a slot. And those 2 things, check and reserve, have to happen atomically as one indivisible action. Hold that word atomically. The whole episode turns on it. Job 2, when playback stops, release the slot so someone else in the family can use it. And job 3, the sneaky one, devices crash, apps get force killed, batteries die, Wi-Fi drops. Those sessions never say goodbye, and their slots have to free themselves automatically. Now the non-functionals, and notice how they pull against each other. First, strong consistency on that counter. No oversell under concurrent plays. This is one place in the whole series we deliberately choose consistency over availability. Second, latency. This check sits on the press play critical path before any video rolls, so it gets a budget of 50 to 100 milliseconds. No more. Third, here's the tension. The system still has to be highly available. If the counter store dies, we cannot take down the play button for 300 million people. And fourth, the limit is global. 4 streams mean 4 across every device and every region on Earth, not 4 per region. One business nuance worth saying in the interview, this limit is effectively hard, but a momentary off by 1 is a business decision, not an engineering failure. Blocking a paying member on a transient error is worse than 30-second grace. That judgment quietly shapes everything we build next. Let's do the numbers because they tell us something surprising. This is not a big data problem. Last episode we sized ingest at roughly a million playback events per second. Now size this one. 300 million members, call it 2 plays each per day. That's 600 million plays. Divide by 86,000 seconds in a day, and you get about 7,000 plays per second on average. Prime time spikes that maybe tenfold, 70,000 checks a second. That's 14 times smaller than Even's ingest, and any decent service handles it. And look at the state. Per account, 1 counter and a small set of active sessions, a few hundred bytes. So where's the difficulty? Right here. All the contention lives inside one account's key. The hard part isn't 70,000 requests spread across the fleet. It's 5 requests hitting the same family's counter in the same millisecond. So the math hands us 4 conclusions. 1. Throughput is easy. We don't need Kafka or an LSM tree here. Different problem, different shape. 2. Contention is per account, which means blast radius of any conflict is 1 household, very tiny. 3. Total state is small enough to live in a sharded in-memory store. And 4. Shard by account ID. So each account's truth lives in exactly one place. That last one matters the most. because you can only be atomic against a single authority. Scatter the truth and you can't. Now the API, and there is one hiding in it that solves the nastiest requirement almost for free. Press play and the client posts to /v1/stream sessions with the title and the device. If there is a room, back comes a 201 with the session ID and this field lease seconds 60. Circle it. If the account is full, a 409 stream limit reached, and notice it carries the limit and the current active count, so the client can render a real screen. Here is who is watching. Go turn one off. While video plays, the client puts a heartbeat every 30 seconds, and each heartbeat renews the lease back to 60. Stop cleanly and delete releases the slot immediately. So what is a lease really? It's a reservation with an expiry date. Your slot is only yours for 60 seconds at a time. Keep playing, keep renewing. And now walk through what happens when a phone dies mid-episode. Heartbeat stop, 60 seconds pass, the lease expires, the slot frees itself. Nobody had to send a goodbye. We just converted clients must release correctly, which is a fantasy on real networks, into the server expires automatically, which is a guarantee. Second, that 409 is a feature, not an error. Designing the rejection path with as much care as happy path is exactly what separates an API that demos well from one that ships. And third, same rule as last episode. Identity comes from the auth token, never the request body, and every lease timestamp comes from the server's clock. Client's clock lie. We never trust them with money adjacent state. Here is where most designs quietly break. So let's break one on purpose. The obvious implementation is 3 steps. Read the active count, check if it is under the limit, and if yes, write count +1 and allow playback. Read, check, write. It reads like correct code. It passes every unit test you'll ever write for it. And between step 1 and step 3, the world is allowed to change. Watch it fail in real time. 8 PM, the Kumar's 5 devices. All 5 requests read the counter within a few milliseconds of each other. And every single one gets back 3 because none of their writes have landed yet. All 5 run the check. Is 3 less than 4? Yes. 5 green lights. All 5 write. All 5 start playback. The counter now says 8 on a 4 stream plan. Every device made a locally correct decision on a stale truth, and the sum of 5 correct decisions was a wrong outcome. This failure has a name worth using in an interview. TOCTOU, time of check to time of use. The value you checked changed before you used it. And here is the part I really want you to internalize. You cannot fix this with faster reads, more retries, or a fresher cache. The gap between check and use isn't a performance bug, it's a structural one. The only cure is to make the check and the use one indivisible operation. So let's build that indivisible operation. We keep each account's active session in a Redis set, and we send Redis a tiny Lua script. Count the set, compare to the limit, and if there is a room, add the session and set the expiry, all inside the script. Why does wrapping it in a script change everything? Because Redis executes commands one at a time per key, and Lua script runs as one command. While this script runs, no other request can touch that account set. The read, the compare, and the write happens with the world frozen. So replay the Kumar disaster. 5 evals arrive at the same millisecond, and Redis simply lines them up. First 4 count, 3 then 4 then 5 then no. First 4 see room and reserve. The 5th counts 4. 4 is not less than 4, returns 0, gets a 409. Deterministic. No lock is acquired. No retry loops, no network round trips, sub-milliseconds. The race doesn't get handled, it stops existing. Now the alternatives an interview will poke at, reject them with reasons. A distributed lock works, but look at the cost. Acquire, read, check, write, release, multiple round trips on your 50 millisecond budget. And now lock expires, lock loses, and fencing tokens are your bugs to own. We don't need mutual exclusions over a workflow. We need an atomic op on one key. A distributed SQL transaction, spanner, cockroach DB is absolutely correct and absolutely oversized. Global acid machinery to guard a few hundred bytes per account. Match the weight of the tool to the weight of the problem. Say that sentence in the interview. An eventual consistency counter. Cassandra counters CRDTs, counts that coverage later, oversells now. That's the exact failure we came here to kill. Wrong model for this flow, even though it was right model for the last episode. Let's put the whole system on one screen and notice how small it is. That's not laziness, that's the design. Devices on the left, every calls land on Zool first, the same front door as episode 1. Authenticate the token, resolve the account, rate limit. One different from even word saying, under overload we shed the heartbeat style traffic first. But these session calls are small, cheap and revenue relevant, so they are protected, not shed. The stream session service is a referee and it is deliberately stateless. Any instance can serve any account, so it can scale flat and fails boring. On play, it reads the plan's limit from the entitlement service, cached, because plans change rarely, then fires the atomic Lua reserve at Redis. Redis holds the only state that matters, per account session sets, sharded by account ID, each account pinned to a home region, every entry carrying its lease TTL. Zombie slots expire themselves right here, no janitor job needed. Step back and look at the shape. The strongly consistent core is one key and one atomic operation. Everything around it is stateless and boring. That's deliberate. Strong consistency is expensive, so you buy as little of it as possible. Below, Cassandra keeps a durable copy of every session, written asynchronously off the hot path. It's the audit trail. It powers which devices are streaming, and it's the recovery source. If a Redis shard loses its data, we rebuild the live counts by replaying the sessions with unexpired leases. And the red node is the headline decision. If Redis is unreachable, we fail open. Allow playback with a conservative cap, page a human. Enforcement must never take down the play button. More on that judgment in a minute. Now trace one session cradle to grave, because the ordering is where the correctness lives. Dead presses play. Post stream sessions hits Zool, resolves the token, which resolves the token to account 42, premium, limit 4. The session service fires the atomic reserve at Redis, count, compare, add. Room available comes to 201 with 60-second lease. Total cost on the critical path, about 2 round trip, single digit milliseconds. Playback starts instantly. Only after responding does the service persist the session to Cassandra asynchronously. Durability without ever making the player wait for it. While the movie plays, a heartbeat lends every 30 seconds, and each one just resets the TTL to 60. That ratio, lease equals to 3 times the heartbeat interval, is worth explaining out loud. One lost heartbeat on a flaky Wi-Fi must not evict a live stream, so the lease survives a single miss. But a truly dead device stops renewing and frees its slots inside a minute. Too short a lease and you kick a real viewer. Too long and a crash slot blocks the family. 60 seconds is the balance point. Credit rolls, dead hits stop, delete removes the session from the set, active drop to 1, and a 204 confirm it, clean open, clean close. Next scene, nothing closes cleanly. 2 war stories, because this is where the design earns its keep. Story 1. A phone is streaming on the train, heartbeat renewing like clockwork. Then the battery dies mid-episode. No stop, no delete, no goodbye. From the server's perspective, silence. In the naive design, this slot is now leaked forever, and the family is down to 3 streams until someone calls support. In hours, watch the TDL clock, 60 seconds left, 30, 0. And Redis expires the session automatically. Slots is back, nobody cleaned up. And that's the point. Correct release isn't an action we hope clients perform. It's a timeout the server guarantees. Self-healing by construction, not by a cron job. Story 2, the double press. The TV posts a session and the 201 gets lost in transit. The TV has no idea it holds a slot, so it retries naively. That's the second session. 1 press, 2 slots burned. Instead, the reserve is idempotent on the account plus device. The retry finds the existing live session for that device and returns it. Same session ID, still 1 slot. Notice the rhyme with the episode 1. There it was a client minted event ID deduping playback events. Here's the account device pair deduping the reservations. Different key, same principles. At least one's delivery plus idempotent handling equals effectively one's behavior. That pattern transfers to every system you will ever build. Last phase, the 4 judgment calls, and these are pure staff territory. 1. It's 8 PM and Redis is down. Fail closed. Reject every play because you can't verify limits. Or fail open. Allow playback under enforce for an hour. Walk the cost. Failing close turns a counter outage into a total playback outage paying members. Failing open costs some temporary limit leakage. Netflix's answer, and the defensible one, fail open with a conservative cap. Alarm loudly and rebuild the true counts from Cassandra when the shard recovers. Never let the enforcement system outrank the product it protects. 2. Global correctness. 4 streams across the whole planet means the authoritative counter per account. Pin each account to a home region. The Kumar account lives in the US East. A member traveling to India pays one small cross-region hop on the reserve call and only on play, never during playback. The alternative per region counters with reconciliation reintroduces the exact oversell window we just spent 10 minutes killing. 3. The planned downgrade. Family drops premium to standard while 4 streams are live. Kill 2 mid-episodes. Never enforce the new limit on the next play. You save nothing by cutting a stream that's already running, and you burn real trust. Flag it explicitly as the product decision you would confirm. Interviewers reward candidates who know which calls aren't purely technical. And 4. The follow-up you should see coming. Can members see who is streaming and kick a device? Look at what we already built. The session set carries device metadata, so the list is a read of that set, and remote stop is just a delete on someone else's session ID. When a feature request lands inside your existing model for free, that's the strongest signal your model was right. 4 patterns to steal. They go way past Netflix. 1. Atomic check and reserve. Any read, check, write done as separate steps is a TOCTOU bug waiting for the traffic. Collapse it into one server-side operation. 2. Leases, not trust. Every grant expires unless renewed, so crashed clients clean up after themselves. That's how you build the self-healing state. 3. Consistency is per flow decision. Eventual for resume points, strong for paid limits. And you say the boundary out loud before anyone asks. 4. When enforcement and availability collide, decide the failure you can afford, and here that means failing open. Next episode is my favorite of the series. You press play and 2 seconds later, video is on your screen. In those 2 seconds, entitlement checks, a DRM license, and a steering service that routes you to cache running inside your ISP's own building. Control plane versus data plane, the episode. If this one earned it, like and share, and tell me in the comments, would you have opened fail, or is a hard limit worth blocking playback for? I'll be arguing in the replies, so see you in the next one.